Okay, while you're sharing the audience, please remember to mute all your microphones and raise your hands if you have questions to pose after the talk. Okay, go ahead, Alfonso.
Okay, so thank you very much for giving the opportunity to share with you some results about dark matter. Today, I want to tell you a little bit about non-abelian vectors in the dark sector. So the outline of this talk is first, I'm going to give some motivation for this work. I will provide some context also. Then I will focus on a model, specific model, which include a scalar dark matter plus gauge interactions in the dark sector. I will show some preliminary results, and I insist that the results are preliminary. I will try to answer the question if is it possible to discover or exclude this model, and at the end I'm going to state some conclusions. Well, of course, it's always possible to include vector fields in a physical model, and the vector fields can play two roles. First, as dark matter fields, it is difficult because in general, massive vector fields induce unitarity problems, unitarity violation in models, that is very well known. But it's possible to make that kind of model consistent. I will talk a little bit about this. But the other possibility is to include vectors like gauge bosons of new dark interactions. Let's focus first on the vector field as dark matter. There are many kinds of vector dark matter models. For instance, some models of dark photons, or some Kaluza-Klein resonances with spin 1 can be a dark matter candidate, etc. But we have studied the case when the dark matter is a neutral component of a weak multiplet in the same path of the minimal dark matter model, right? But in this time with the vector field as playing the role of dark matter. Until now, we have studied the case of the fundamental and the adjoint representation of SU2. And as an example, just as an example from the adjoint case, I will show this picture. This picture represents the allowed parameter space. This is the mass of the vector boson, the neutral vector boson. And this is its coupling constant to the Higgs boson. And this is the allowed parameter space after all the experimental constraints were applied. This is a work with Sasha Beliaev, Giacomo Cacciapaglia, James McKay, Dixon Marine, and myself. So you can see that a vector with masses around 3 TeV and with coupled to the Higgs with strength not too high, it's allowed. Some details about these massive vectors in the adjoint representation. The idea started with realizing that the theory of massive vector coupled to a massless gauge boson may be compatible with unitarity, at least at tree level, provided that the massive vector is protected by a Z2 symmetry. This is a result I got almost 7 years ago. When the symmetry, the gauge symmetry is spontaneously broken, the mass of the gauge bosons and the coupling of the massive vector to the Higgs boson reintroduce unitarity violation. However, this unitarity violation can be under control. For instance, I show you here the scale of unitarity violation as a function of the mass of the vector dark matter and the coupling to the Higgs boson. So in the range where we can saturate the dark matter relic density, the unitarity violation scale is around 10,000 GeV, 10 TeV. Sorry, 10,000 TeV. So it's under control for phenomenological processes. Well, now I'm going to focus on vectors as gauge bosons in the dark sector. Why to consider this case? Well, we want to study models with the following feature. First, we want to study a complex model for the dark sector. I mean by complex, a dark matter model with its own interactions. I mean with a dark sector like the standard or visible sector. I mean with their own interactions. We want a model that could be ultraviolet complete with non-abelian gauge interaction in the dark sector, and we want to avoid interactions between the dark matter and the standard model via hypercharge. So our proposal to do that is to consider a scalar field which is a triplet of a dark SU2 group. This is a new group, okay? New SU2 group. The spectrum is similar to QCD, to low scale QCD. I mean, we have a triplet scalar like the pions and massive vectors like the rows in QCD. And this work is in collaboration with Sasha Beliaev and Felipe Rojas Abate, a former student. The structure of the model is the following. We have two groups, SU2, and of course we have the hypercharge group. We need a bi-doublet scalar field in order to break down these two SU2s into the SU2 of the standard model. And we put all the standard fermions and a scalar doublet, which is the usual Higgs doublet, right? Transforming under the first SU2, and we introduce a new, sorry, this is wrong here. This should be a triplet. An additional scalar field, which is a triplet, not a doublet, as is shown here. Sorry, it is a mistake. A triplet, a scalar triplet, transforming under SU2. this scalar field, the capital phi, get a wave at a scale u, while the usual Higgs get a wave at the usual scale v, and a is the ratio of the two scales. This is the Lagrangian of the model. I will not insist very much on it. This is a mess. I will not bore you with these details. So the results. This picture shows some prediction of relic density for several values of some coupling constant. Alpha 1 is the coupling constant which relates the scalar triplet with the Higgs bosons. And this is the mass of the dark matter candidate. We see that for representative values of the parameters, we achieve the observed relic density, we saturated the relic density at masses of the order of a few TeV. Why is that? Because, well, in general, when you have a scalar dark matter, you can achieve the observed relic density at a lower mass of the scalar dark matter. But in this case, the presence of the gauge interaction in the dark sector produce a very efficient annihilation channels. So you need a more massive dark matter in order to get the right relic density. You can see the annihilation into the dark gauge bosons, for instance. Here is an annihilation into or mediated by the heavy scalar. In the relevant mass range, in the range of a few TeV, we show that the scalar dark matter is out of the sensitivity of xenon one tone. So we explain why this dark matter has not been discovered yet.
Alfonso, you have 2 minutes left.
Okay. Here I show some scanning of the parameter space, but I will concentrate on the parameter space which allow, after all the experimental constraints are applied. So we see that there is a beautiful parameter space which remains available. This is the coupling of the dark matter to the Higgs, and this is the mass of the dark matter. Here we show the parameter space in terms of the dark matter mass and the dark gauge boson mass. So the dark gauge bosons needs to be very massive, with masses around 10 TeV. At colliders, it's very difficult to discover this this model. The main production channel of dark matter is in association with the charge companions. These companions are long-living particles, and the LHC can exclude this companion, the model, for masses of the charge scalar below 700 TeVs, which is far from the area of interest. But the indirect search has a possibility. This is the region of interest with masses around some TeV for the dark matter. And we can see that for representative values of the parameters, this model can be confirmed or excluded by CTA, for instance. So I will move to the conclusions. The vector resonance provides a very efficient annihilation channel for the dark matter. This push their mass, the mass of the dark matter, to the TeV sector in order to satisfy the observer gradient density. It is difficult to discover the dark sector in collider and direct detection in this range. But indirect detection, in particular CTA and SWIGO, has a chance. And I think that this is a general feature of models with gauge interactions in the dark sector. Thank you very much for your attention.
Okay, thank you, Alfonso, for this nice presentation of your proposal. Are there questions? I don't see a raised hand for the moment. Giovanna, go ahead.
Oh, hi. Hi, Alfonso.
Hi, Giovanna.
I was interested in your collider constraints. You show upload as a function of the lifetime of this charge scalar. So which experimental search are you thinking about for making those constraints?
Well, we are thinking about searches at the LHC. Sasha Beliaev is member of CMS, so he knows very well the possibilities that CMS has in.
But is it this disappearing charge tracks search?
Yes, this is disappearing. Okay. Yeah, this is disappearing tracks.
Okay.
I'm sure you will teach us about that in your presentation.
If I have time, I also have a dark matter model with that particular signature. So I just wanted to know if it was the same. Yeah.
Okay.
Good.
A very good setup of Giovanna's talk later today. Are there other questions? I don't see any. So let's thank Alfonso again.